Okay, so let us again go through what we have already seen about matrices so far. So what we have seen is this. Say we consider an n-dimensional vector space V, and say we consider an ordered basis of V, ordered basis for V over F. F is of course the underlying field. And then we consider a linear operator T on V, and say the effect of T on the basis elements be this, where each such image has been expressed as a linear combination of the basis elements again, and the scalars alpha ij have appeared. Then we know that the matrix of T with respect to this ordered basis is given by this. It's this square array. Now normally when we write matrices, we do not write the entire array because it's cumbersome to write it fully. I mean, even in this fashion also, where we actually do not write all the elements, but still it is somewhat cumbersome. So instead, we are going to write the matrix empty like this, showing its general element alpha ij. Now, because of the way we have arranged the scalars as a rectangular array, it looks like a table, so naturally it has rows and columns, and accordingly they are also called so. For example, the first row consists of these entries, alpha 1 1, alpha 1 2, alpha, and so on up to alpha 1n. For the entries lying in the first row, in the double suffix, the first number is 1, that is the row number, and the second number is the position of the entry in that row, in what column it lies, it indicates that number. For example, here the second number 1 indicates the fact that alpha 1 1 lies in the first column. Because the first number is 1, so it lies in the first row, but because the second number is also 1, it lies in the first column. Similarly, alpha 1 2 indicates the fact that it is an entry, it is that entry which lies in the first row due to the first number being 1, but because the second one is 2, so it lies in the second column, and so on. Okay. Now, we are interested in calculating the matrix of the sum of two linear operators. Can we do that from the matrices of the original operators? So that is the next thing we are going to see. So the setup is same. V is still an n-dimensional space, and we have considered this ordered basis for V. With respect to this ordered basis, we are going to calculate the matrix of the sum of two linear operators. So let's consider two operators. Let S and T be two operators on V. This part, you just forget about this T, okay. This we just simply wrote so that we could recall what we did in the previous video. So the matrix of T is this, it's just a general thing. But now we have considered two operators freshly, okay. So these are just some operators, S and T. This T, it was just for discussion. And I am saying this because now the matrix of T will not be alpha ij, it will be something else. This is a new discussion. Okay. We want to find the matrix of S plus T. That is our aim now. Okay. Also, let the matrix of S be sigma ij. Actually, the author has used round brackets because to enclose the entries of any matrix, he has used round brackets. But because I have used square brackets, so here also I am using square brackets. and let the matrix of T be one whose ijth entry is tau ij. And there are some other terminology here as well, which I don't think needs any mention, because almost all of us are well familiar with matrices. I mean, it's not that we are looking at this for the first time. Still, this alpha ij is called the I comma jth entry of this matrix. This is something we already know. That's why I said MT is the matrix whose ijth entry is tau ij, say. Then, by the rule by which these matrices are formed, we should have this. Vis should be equal to summation sigma ij vj. Okay. And where j is varying from 1 to n, because the suffixes, whatever suffixes we are going to consider, are going to vary from 1 to n, so there is no need to mention this again and again. Okay, so we can simply write j. It's understood that this sum varies for j from 1 to n. That 1 to n part, there is no need to write that. That's understood. It's not going to change. I stays fixed here. Fixed means for this sum it's fixed, but I of course changes. Within this sum I is fixed, but I of course changes like this. Which of course, okay, yeah, before writing this though, I could have written that other thing also simultaneously. And Vit is equal to summation tau ij vj, and the summation varies over j. Now I can write for all these i's. Okay, so and that is why, because of these things, these equations, actually we have the matrices of S and T like this. Now, our aim is to see what S plus T does to the basis elements. So by the definition of addition, this is VIS plus VIT. Oh, I have the habit of writing alpha straight away. Here we have sigma ij vj plus tau ij vj. If you find working with these summation notations somewhat problematic, you can write the sums fully. Okay, fully means actually as a sum you can write. Of course, you have to use that ellipsis dot dot dot, because here n is a general positive integer. But still, if you find this somewhat difficult to understand, you can work with those, that kind of notation. However, you would have to write a lot for that. And it's advisable that you become familiar with this and you get comfortable with this type of notation. Because you see, the more you work with these things, eventually you will find that it becomes overwhelming if you do not use this summation notation. Okay, so now what do we get from these two using the properties of a vector space? Using the fact that vector addition is commutative, associative, and also using the other axioms for a vector space, we get that this sum is equal to summation of sigma ij plus tau ij phi j. And that final expression is actually a linear combination of this phi s plus t, linear combination of the basis elements for vi s plus t. Hence, and here of course I varies like this, that is understood, that also we are not writing. Whatever is understood and need not be mentioned more than once, we won't mention. Okay, that will save space and effort. Hence, we can see directly from this that the matrix of S plus T with respect to our chosen ordered basis, all the VI's, is, I think the author has given it a name. Okay, the name part we will come afterwards. So its ijth entry is simply sigma ij plus tau ij. Note carefully that this is one matrix. Okay, it's the matrix of S plus T with respect to our chosen ordered basis. And its ijth entry is sigma ij plus tau ij, which is the sum of the ijth entries of the original matrices, the matrices for S and T. Okay, so this is pretty straightforward. So sum is not complicated at all. To find the matrix of the sum of the two operators, you just take the sum of the ijth entries of the matrices of the operators. That's it. Pretty straightforward. Okay. Next, for any scalar gamma coming from the field, what shall I get if I try to calculate, well, not this one, but this, say, Vi gamma s. I mean, I can multiply the operator s by the scalar gamma, that is allowed because the operators form an algebra. And in an algebra, we have addition of vectors, multiplication of a vector by a scalar, and multiplication of vectors as well. So I can multiply this vector s by a scalar gamma. By definition, this is what? Gamma times Vi s. So that is just this sigma ij pj, where the sum varies over j. And now again using the axioms for a vector space, first you can take gamma inside this sum, and then gamma times sigma ij pj can be written as gamma times sigma ij, that scalar, times vj, using one of the axioms for a vector space. So ultimately the sum will look like this. In order to emphasize the fact that here the coefficient, the scalar by which we have multiplied Vj is this product. That's why I have used brackets. Okay, so just like that equation, now we have expressed Vi gamma s as a linear combination of the basis vectors. So from this I can write the matrix for gamma s. This is also going to be extremely straightforward. So it's just this. So M of gamma s is that matrix whose ijth entry is going to be this gamma times sigma ij. So here you just have to multiply the ijth entry of the matrix of S by gamma. That's it. However, there is one somewhat complicated thing, which is the matrix of the product of S and T, ST. That is the thing we are now next going to calculate. Next, this calculation has to be done somewhat carefully. So let's just go through the details and see what we get. So according to the rule, we have to see what VIST becomes. By the definition of, you see, here multiplication means what? Multiplication means composition. So this is just VIS of T. Alright, now we know what VIS is. VIS is what? Summation of sigma ij Vj, and the sum varies over j. However, because we have to calculate another thing, I mean the effect of T on that, so we don't use j, but we use another name for the second suffix. Say we call it k. That means now VIS becomes this summation sigma ik. It's just for convenience. Instead of calling it k, you can call it something else. In fact, you can call it j itself. But then when you apply t on that and then write a similar sum for the t images, then you won't be able to use j there. You will have to use something else. But anyway, we are using k here. So the sum varies over k. Again, understand that here all the suffixes vary from 1 to n. That's why we are not writing anything. T. Now, what is this? This is after all a linear combination of the basis vectors Vk, on which we are applying t. Because t is a linear operator, this is simply this. And now we also know what Vkt is. This itself is also a linear combination. It is this linear combination. Summation tau, note that here we have k. So the first suffix is k. The second suffix we have chosen j. Okay. Vj. And here the sum varies over j. Alright. Now I will go through some steps which may seem a little complicated to understand, but we are going to justify the steps. So what I first do, I will of course offer some justification, but it may not be immediately clear. Okay. So the first thing is we need to understand what we are looking at. You see, in this expression we have two sums, this inner sum and this outer sum. The inner sum has the scalars tau kj, vj are the vectors, and outside we have sigma ik, which are scalars. So if you forget about the outer sum for a moment and think of the inner sum only, then you are multiplying this linear combination of the vectors vj by the scalar sigma ik, which can be taken inside. Inside means first you take the sigma ik inside, multiply with each such scalar multiple, and then in another step, you can combine sigma ik and tau kj as a product of two scalars, and by that you multiply Vj using one of the vector space axioms. So instead of doing this in two steps, we can do them in one step, like this. Sigma ik tau kj, the fact that we are considering the product of these two scalars, it has been emphasized by the use of these brackets. And then we have Vj. Okay. Now because we are dealing with finite sums, in each sum the index varies from 1 to n, and that is why we can switch the sums. This goes outside, this goes inside. It's a fact about finite sums. It's called Fubini's theorem for finite sums. But forget about those names, Fubini's theorem or whatever. This is not always the case for infinite sums or infinite series. For finite sums, we can switch the order. Okay, so if we assume that fact, then we can write the two sums like this. And then there will be some j's, there will be some vj's where j is just one j. So what I am trying to say here is that if you collect from this sum those terms that are coefficients of Vj, then you can write all those scalars together as a sum. That will be multiplied with Vj, and you will get this. See, the difference between this one and this one is that here this is the coefficient of Vj. So what I am trying to say here is that in the previous sum, there will be many such terms which all contain Vj. So from all of them, to put it in simple words, we take Vj common out. That gives us a sum of some coefficients. That is this sum. Now of course, in this somewhat abstract representation of these sums and all these things, it's actually a little difficult to really see what is going on here. And that is why let us take a small example and do the calculation in that example. That will make everything clear. Okay, we do not have to rely on vague understandings and general things. Let's take a specific example that will make this entire thing clear. See, this is one of the rare advices which is actually something very simple when you think about it, but we often neglect it. And the advice is, when we are dealing with something really complicated, just take a simple example and see how the thing works out in that example. It's an advice given to me by one professor somewhere. Okay, I met her. This is a golden advice. It has saved me more than once. Alright, so what shall we do? Let us consider this value of n. Because you see, in these sums, n is what determines the size of all the things. Okay, so in all the sums, the suffixes vary from 1 to 2. We are not taking 1 so that we get some amount of non-triviality. Alright, so there is of course no point in writing these things. Where shall we start? We shall start here. Okay, it's because after this we have switched the two sums. But you may be wondering if that is really possible or not. So let us start with this. And let us this time actually write what all the things are. So we have sigma ik. We don't know what I is. Let's just keep it as I. And then we have j varying from 1 to 2 tau kj vj. Okay, so that thing is just this thing, but with n equal to 2. Now what is this actually? It is just this. So it's actually what? It's a sum of two terms. I mean, I'm talking about the outer sum. One of the terms has k equal to 1 and the other term has the value k equal to 2. So for k equal to 1 we get this I1 summation j varying from 1 to 2. Remember k is 1 now, so 1j vj plus, and then we have another term where k is 2. So sigma I2 summation j varying from 1 to 2. This time we have tau 2j vj. But these themselves are also sums. So sigma I1 tau 1 1. Now you write this sum out fully by varying j. This is 2, the upper bound of the sum. Okay. Tau 1 1 v1 plus tau 1 2 v2 plus sigma I2 tau 2 1 v1 plus tau 2 2 v2. Okay, so according to this calculation, these steps actually we are doing for ourselves. These steps are not available here because we haven't really said here what these things are. I mean, in this special case we are seeing what the things actually are. Okay, but then it's not actually this sum that I have written, no? I mean, not this step, but I have actually started from here, okay. And now I have to multiply the things out by sigma I1, sigma I2 using the properties of a vector space. So if I do that, I will have this. Sigma I1 tau 1 2 v2 plus sigma I2 tau 2 1 v1 plus sigma I2 tau 2 2 v2. And then I was telling something about taking vj common out, right? And have a scalar like this that you can see here. From these two terms, the first term and the third term, you have this sigma I1 tau 1 1 plus sigma I2 tau 2 1 v1 plus, and then from the second and fourth term you get sigma I1 tau 1 2 plus sigma I2 tau 2 to V2. Now if you again rewrite these terms using summation notation, what do you get? First of all, let us write the immediate sums as using summation notation. So this one can be written as sigma ik tau k1, where k varies from 1 to 2 v1 plus, then this one is sigma ik tau k2, again k varies from 1 to 2 times v2. But then this sum itself, the outer sum, can be written using summation notation like this: sigma ik tau k. But now this second number also we are varying. In the first term it is 1, in the second term it is 2. So we call it j. And here in the inner sum k varies from 1 to 2. Outside we have the vector vj, and now j varies from 1 to 2. Because everything just varies from 1 to 2, so there is no point writing that. Now you match this one and this one. You see, the outer sum varies over j, the inner sum varies over k, and the term is sigma ik tau kj, and we have vj. Okay, so that's how for a small value of n, the calculation is this. And from this, and maybe from another similar calculation for the value n equal to 3, you can see that in the general case also this will work out. And that's how you have the calculation. That is the justification for the calculation. All right. But now, what is the end result? The end result is this. Do not forget what we started with. We started with this VIST. We have found that that is equal to this linear combination of the basis vectors Vj. So the matrix of ST with respect to our ordered basis is, let us give it some names, say mu ij, whose ijth entry is nu ij, where the ijth entry is this, the scalar of Vj in this equation, in this linear combination, where nu ij is summation sigma ik tau kj, where the sum varies over k. This is the most complicated of the 3 operations. But it's just this, and in this form it looks very complicated, but if one thinks about it, what exactly, how are we getting this ijth entry of MST? You see, in the matrix of S, whose ijth entry is sigma ij, you have the ith row, which looks like this. Okay. Oh, I should maintain consistency because I am consistently using square brackets. So this is the ith row of this matrix. Similarly, we also have the matrix of T whose ijth entry is tau ij, and the jth column of that matrix, of this matrix, looks like this. And this ijth entry of the product of those two operators, I mean its matrix, is actually the dot product of this row and this column. It is that dot product which you get from vector analysis. If you recall your vector analysis from school, there you have come across dot products like this, right? Say you have two vectors I cap minus 2j cap plus 3k cap. Okay, I am talking about vectors that we know as vectors, actual physical vectors, and say I cap plus j cap plus k cap. Their dot product is calculated like how? I mean, there is a definition for the dot product. Using properties of dot products you can calculate, but there is a rule also which is a consequence of those properties. You multiply the corresponding scalars of these unit vectors. That is, here the scalar is 1, you multiply that with this one. Here the scalar is minus 2, you multiply that with 1. Here the scalar is 3, you multiply that with 1. And you take the sum of all those multiples. That's what we are doing here also. I mean, of course, we have a row and we have a column, but you can do not concentrate on rows and columns, I mean, them being different kinds of objects. You just concentrate on the entries in those rows and columns. So sigma I1 gets multiplied with tau 1j, sigma I2 gets multiplied with tau 2j, sigma I something gets multiplied with tau that something j, and that something in general appears as k. That's why it's like this, sigma I k tau kj, and the sum of all such terms as k varies from 1 to n or from 1 to whatever the size of the situation is. Okay, so that is the method for calculating the ijth entry of the matrix of the product of two operators S and T. Now here we have a small example to see how that works out when we have concrete values. Although we are assuming that almost all of us are familiar with matrices, but for the sake of rigor, we are treating these things as if we don't know about matrices, and this is the first time we are introducing them. Okay. Now, say your MS is actually this matrix. 1, 2, 3, 4. Okay. Yeah, you can take anything, but this is a convenient choice. 1, 2, 3, 4. And say MT. I mean, these are things the author has considered in the book. -1, 0, 2, 3. So according to this rule, what will be MST? So MST is this new 1 1, new 1 2, new 2 1, new 2 2. And to calculate these new ij's we have that row. For example, to calculate new 1 1, we have to consider the first row of this matrix and the first column of this matrix, which are what? Let's just write like this. The first row of ms is 1 2 and the first column of mt is minus 1 2. If we carelessly write like this, okay, we are not actually allowed to write anything like this because nothing like this has so far been defined, but just for the sake of seeing what happens using the row and column. So what do you have to do here? Multiply 1 with minus 1, that gives you minus 1, and multiply 2 with 2, that gives you 4. You take the sum of them using this formula, so you get 3. Okay, so this entry is actually 3. Similarly, what will be new 1 2? New 1 2 will involve, the calculation will involve the first row of ms and the second column, because here you have 2, of mt, that is 0 3. So you multiply the first one by the first one, which gives you 0, and the second one by the second one, which gives you 6. So you get 6. That means this entry is 6. Alright. Next, new 2 1 similarly involves the second row of ms, that is 3 4, and the first column of mt, minus 1 2. 3 times minus 1 is minus 3, plus 4 times 2 is 8. So this is 5. That means this is 5. Then finally you have to calculate new 2 2. So new 2 2 involves the second row of ms and the second column of mt. 3 times 0 is 0, plus 3 times 4 is 12. So this is 12. So that is the matrix of the operator st, 3 6 5 12. Alright. Now, so we have seen what happens when we try to find the matrices of S plus T, gamma S and ST. Alright. And these findings give us clues for defining some operations among matrices themselves. And these findings guide us exactly how to do so. So for that, let us now treat the matrices themselves as objects of interest and then define on the set of all possible matrices operations that would correspond to these 3 operations that we have in the algebra AV. So we write like this: let F be a field, a matrix means actually an n by n matrix. Yeah, we need to mention the size. An n by n matrix over F. These are some terminology that we use while talking about these things. Is a square array of elements in F. And that square array we already know how it looks. Which we write briefly as this. Okay. So such objects are called matrices. Now we are going to give some name to the set of all matrices that can be considered in the present situation. The set of all such n by n matrices over F is going to be denoted by F suffix n. Like this, and its elements are the n by n matrices, all of whose entries come from F. Alright, so now we are going to define some operations on this set Fn, whose Q have been taken from the previous considerations, the calculations. But before doing anything to F, we need to first of all say exactly when two elements of Fn are considered equal. See, this is one thing that you should always remember. Say you have defined some new kind of mathematical object, and for some reason you consider the set of all such objects. Now on that set, naturally you will want to define maybe some algebraic operations or maybe some topology, some measure, something. But before you do anything though, you have to first of all carefully define a notion of equality on that set. Exactly when are you going to call two objects from that set equal? And do not think that this is something very easy always. There are some axioms that need to be followed here, but I am not going to go into the details of those things, okay. The equality relation that you are going to define on a set needs to be an equivalence relation, and there is something else also. But let's just forget about that. The thing you should remember is that always first say when two objects are equal. And here we are going to do that like this. For any alpha ij belonging to Fn, okay, simply one alpha ij is not enough now. We would need two alpha ij and beta ij belonging to Fn. We have these things. We declare the matrix alpha ij to be equal to the matrix beta ij if and only if alpha ij is equal to beta ij for all I and j. Remember, no matter how sensible this definition of equality may look, but this is not the only possible definition of equality. There are other ways also you can define equality. Then the meaning of equality will change, but then again, in the background of those definitions also, some axioms have to be satisfied. For all I and j. Why am I stressing so much on equality? It's because you see, when your system changes, the definition of equality also may change. Let me give you one example. Say you consider this, what can I take? Yeah. You consider these two integers 3 and -7. In the system of integers, they of course are not equal. However, if you treat them as objects in the system of integers modulo 10, then they become equal. Okay, so that is why the definition of equality can change. It depends on the situation. But anyway, so we move on. We define a sum of two matrices to be the matrix, and the author has used lambda here. You can use anything you want, where, remember, these are operations we are defining now for the first time, okay, on the set of square matrices. Once they are defined, then only we can use matrix addition, multiplication, those things. Where previously these things were not available to us in this book, although we did use matrices in some examples before. But other than that, formally this is the first time they are being defined, where lambda ij is alpha ij plus beta ij for all I and j. Then number 3, multiplication of a matrix by a scalar for any gamma belonging to F. We defined gamma times alpha ij is equal to mu, where mu ij is gamma times alpha ij for all I and j. Why am I being so careful to see what Greek letter the author has used? It's because you can watch this video and match it with the text. Okay, so that's why I am not using something else. And finally, we defined the product of these two matrices to be the matrix whose ijth entry is new ij, where new ij is equal to summation alpha ik beta kj. where k varies from, if you want you can use it, k varies from 1 to n, or you can simply write k if it's understood how the variation works. So these are 4 things we have defined on Fn. Now the way these things have been defined, these definitions have been dictated entirely by what we did with the operators and their matrices. So you can imagine this happening. Let V be an n-dimensional vector space over F, and let this be an ordered basis or V over F, okay, for any t belonging to A of V, means home V comma V, same thing. We associate with T its matrix M of T in Fn with respect to the basis. Okay, so first we have Fn, we have defined Fn, and then we defined all these operations, equality, everything in Fn. So Fn now takes on a life of its own, an algebraic life, in which it is a set, it has its own definition of equality, it has its own 3 operations. And then we are bringing back operators. On one hand we have Fn, on the other hand we have an n-dimensional vector space V, and we have chosen an ordered basis for V over F. Then for every t, every element in A of V, we are associating with that a matrix MT, which is what? It is the matrix of T with respect to this. And the way this association works, and because we have used this association to define those things on Fn, so this association gives us an algebra isomorphism from the algebra A of V onto Fn. This association gives us an algebra isomorphism of A of V onto Fn. And from that one can immediately see that because of that Fn itself becomes an algebra under those operations. So Fn is an algebra, and associative algebra of course, where the multiplication is associative. An associative algebra over F. Actually, there is a reason for calling these structures associative algebras, because there exist structures where all the rules of algebra are there, but the multiplication is not associative. One such example is if you consider your 3D vectors with the cross product of vectors. If you take that product as your product for algebra, you get a non-associative algebra. But anyway, so you have this association. And note, of course, that this entire thing depends on your choice of the basis. So you change the basis of V, the association changes, because then the T that you choose from A of V will be associated to a possibly different matrix in Fn. That will be determined by the choice of your basis. So, but we do know that whatever basis we choose, that is going to give us an algebra isomorphism of A of V onto Fn. So you keep changing your basis of V, you get new algebra isomorphisms. Every choice of a basis for V over F, we get an algebra isomorphism of A of V onto Fn. And this Fn is, it has a name also, because now we have understood that it is also an algebra. It's called the algebra of n by n matrices over F. It's of course understood why we choose to call it so, because its elements are matrices, so it's the algebra of matrices, or matrix algebra in short. And this entire thing has been stated as a theorem. And the theorem, of course, goes like this. The set Fn of all n by n matrices over F forms an algebra over F. We do not every time mention associative algebra, because we do not consider non-associative algebras in this book. If V is an n-dimensional vector space over F, then any ordered basis, I do not fail to mention the fact that the bases have to be considered ordered. Okay, we have already seen why that is so. Any ordered basis for V over F sets up an association between A of V and Fn, or rather I should have said sets up the following association, but you understand what I am talking about. For any T belonging to A of V, let Mt be the matrix of T with respect to this basis. we then have the association which associates with T the matrix empty, and this association is an algebra isomorphism of A of V onto Fn. Okay, so this is the statement of the theorem, where we have actually restated all the things we have seen today. Okay. Now, because these two algebras are isomorphic, so they are treated usually as the same thing, as the same algebra. So you can either talk about an operator or its corresponding matrix. So a matrix itself is also treated as a linear operator. But keep in mind that behind every such association there must lie a basis which we do not change. Okay, once we fix the basis, that gives us an association. And then some things about matrices. Under this association, the operator which is the zero operator, which maps every element of V onto the zero vector of V, corresponds to the 0 n by n matrix, which becomes the zero vector in the algebra Fn. The zero operator in A of V corresponds to the zero matrix, 0 n by n matrix in the algebra Fn, which we often denote simply as by 0. And the unit matrix in the current context where n is fixed is that matrix which corresponds to the identity operator in A of V. And that matrix you already know how it looks. Its leading diagonal entries are all 1. By leading diagonal we mean this, where the entries are alpha I, where those those suffix values are the same. For example, this is alpha 1, 1, alpha 2, 2 and so on. So all those leading diagonal entries are 1, and all the off diagonal entries, the entries which are not the diagonal entries, they are 0. I urge you to actually see that this is the case. You take the identity operator from here, you take any basis, ordered basis, and calculate the matrix of the identity operator with respect to that basis. You should get this one. And because of our algebra, isomorphism, because we know that the unit element in the ring AV is that identity operator, so its corresponding image in Fn, which is this matrix, should be the identity operator in this ring, which is in fact the case, as can also be directly verified. And this matrix is sometimes also called the identity n by n identity matrix. It is denoted either by in if you want to emphasize the n, but if n is understood simply by I, or sometimes even by 1 also. Okay. And because of this association again, T in A of V is invertible. We already know what this means. Okay, if it has an inverse, or if it is a unit in the ring AV under the operations addition and multiplication of operators, if and only if the matrix of T is invertible in the matrix algebra. This is also a ring, so as an element we can ask if MT is a unit, that is whether it has an inverse under multiplication. It turns out that we have isomorphism, and this is the association T with MT, MT with T. T is an invertible operator if and only if MT is an invertible matrix. And one can prove this also using this association directly. Oh, there is one more thing that we forgot to say. If you still follow the association and see one last thing, you can consider scalar multiples of the identity operator. That is, if you consider a scalar alpha from the underlying field, you can then consider the operator alpha I. It turns out that the matrix of alpha I with respect to your given basis looks like this, where the leading diagonal entries are all alpha. Here they were 1, here they are alpha. And these matrices have a name. They are called scalar matrices. Okay. Scalar matrices are those matrices where the leading diagonal entries are all equal and the off diagonal entries are all 0. So this is a special case of scalar matrices. These matrices, it turns out, commute with every matrix of Fn. Okay, but the converse is also true. Every matrix that, any matrix that commutes with all the elements of Fn turns out to be a scalar matrix. It cannot be anything else. Okay, so they have some kind of special role to play. So that's just about it in this association that we have set up between operator algebra on one hand and matrix algebra on the other hand. So in this sense, they are actually the same thing. But then the next question that arises is, okay, fine. In all these things, you have kept that underlying basis the same. But what happens if you change your basis? Say you have an n-dimensional vector space. You have chosen a basis for it, something. Okay. And that basis has given you an algebra isomorphism between A of v and Fn. Because you can go from AV to Fn, and if you can also come back. So I am using this. Okay, 2 arrowheads in both ways. But now if you change your basis, then also that new basis also gives you an algebra isomorphism. What is the relationship between these two? In particular, if you consider T in A of V, the first algebra isomorphism will give you a matrix of T, and the second algebra isomorphism will give you another matrix of T. Because the bases have changed, the matrices will likely be different. What is the relationship between these two matrices? That's the next thing we will discuss in the next video. So that's just it for tonight. So see you in the next video with new things. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.